Let's talk about sequences. So first, let me give you the definition of what a sequence is. A sequence is simply an ordered list. So for example, if we looked at the sequence 1, 4, 9, 16, 25, 36, and 49, which you might recognize as being all of the perfect squares listed from 1 to 49, here's what I want you to notice. They're in a specific order, so this is the first term. A lot of times we refer to the entries in a sequence as A. So A sub 1 is our first term, and A sub 2 is our second term, and A sub 3, 4, 5 is our fifth term, and so on. So it's simply a list where the order of the entries matters. The sequence you're looking at here has a starting point and a stopping point, so this would be a finite sequence. On the other hand, if I made the list, the sequence 1/2, 1/3, 1/4, 1/5, 1/6, and I put ... I still have a list, an ordered list. So A1, our first term is 1/2, and A4 is, let's see, 2, 3, 4, is 1/5 in this one. And this goes on forever, so this would be an infinite sequence. Now, these might look like patterns to you, the list of all perfect squares and the 1/3, 1/4, 1/5, 1/6. And in fact, a lot of times we give ourselves formulas for these sequences. So let's take a look at some of those. Okay, let's take a look at the sequence whose terms are defined by the formula a sub n, so the nth term, is given by n cubed plus 1. Now, depending on how the homework is written, you could also have this written with the braces notation, which also means a sequence, n cubed plus 1 inside the braces. That means the same thing. And let's say our directions are to write the first 4 terms of this sequence. Okay, so a sub 1 would be the first term, and in this sequence where we're given a formula, we're just going to plug in n equals 1. 1 cubed plus 1 is 1 plus 1, which is 2. So I'm going to write this in, sequence notation. 2 is our first term. A sub 2 means plug in n equals 2 into our formula. So 2 cubed plus 1 is 8 plus 1, which is 9. Okay, 2 more. A sub 3 is 3 cubed plus 1. So that's what, 27 plus 1 is 28. And finally, a sub 4, 4 cubed plus 1, that's 64 plus 1. We get 65. Okay, so there are the first 4 terms of this sequence. What I can't tell from the directions is, does the sequence end after 4 terms or does it go on forever? So usually the sequences we deal with in this class go on forever. And the only difference would be we write ... at the end of them. Okay, let's do another one. Let's write out the first 4 terms for the sequence where a sub n equals n plus 3 divided by n. Okay, we're going to do the same thing. A sub 1 means for the first term, we're going to plug in n equals 1. So 1 plus 3 over 1 is 4. Second term, plug in n equals 2. 2 plus 3 over 2 is 5 over 2. Third term, a sub 3. 3 plus 3 over 3, lots of 3's, is 6 over 3, which reduces to 2. And the fourth term would be 4 plus 3 over 4, or 7/4. Okay. Typically, if the sequence is finite, we tell you where it stops. So if they don't say so, it's probably an infinite sequence. Now doing this, where we're plugging in n values and listing out what the sequence values are, might feel really familiar. In fact, it might feel just like function notation that you've used before, where you are given an f of x formula and you plug in your values for x. In fact, the only difference between sequences and functions is that the inputs for sequences have to be positive integers. So the inputs for our sequences, n, have to be positive. Wow. Let's try that again. Integers. So I would not ask you for the 3.2 3-point-second term. There's no such thing as a 3-point-second term. There's the first, second, third term, and fourth term, but there is no 3-point-second term possible. So all of your inputs are going to be nice, pretty, positive integers. Let's do a couple more examples. So when we're writing out the first 4 terms, let's say we're writing out the first 4 terms, and we'll define the sequence to be b sub n, and we'll make this one negative 1 to the n times n squared plus 2. Okay, so again, we're just writing out the first 4 terms, so we want the first term, second term, third term, and fourth term. And those give us all of our n's. So when we take n equals 1, we have negative 1 to the 1, 1 squared plus 2. Okay, negative 1 to the 1 is negative 1. And 1 squared plus 2 is 3, so our first term is a negative 3. Plugging in n equals 2, negative 1 squared, 2 squared plus 2. Negative 1 squared is positive 1, and 2 squared plus 2 is 4 plus 2, which is 6. So we have 6. Then when n equals 3, negative 1 to the third and 3 squared plus 2. So negative 1 to the third is negative 1. 3 squared is 9 plus 2 is 11, negative 11. And last one, negative 1 to the fourth times 4 squared plus 2. Negative 1 to an even power is positive 1. 4 squared plus 2, 16 plus 2 is 18. We get 18. Great. This sequence is what we would call an alternating sequence, because the signs are alternating positive, negative, positive, negative. That comes from that negative 1 to the n. Okay, let's do another example. Okay, let's say a sub n is equal to negative 3n plus 1, and a couple more times I want to write out the first 4 terms. So the first term, a sub 1, plugging in n equals 1, I have negative 3 times 1 plus 1 is negative 3 plus 1 is negative 2. And second term, negative 3 times 2 plus 1. Negative 6 plus 1 is negative 5. plugging in at n equals 3. Negative 3 times 3 plus 1. Negative 9 plus 1 is negative 8. Okay, now I intentionally didn't write in the next term. Take a look at the list we have going. Negative 2, negative 5, negative 8. I bet without even plugging in n equals 4 to get the fourth term, you might be able to figure out what goes in the next term. Notice that each one of these, you're subtracting 3 in each one of them. So the next term probably is a negative 11, but let's double check that. Negative 3 times 4 plus 1, sure enough, negative 12 plus 1 is negative 11. So each term, you get the next term by subtracting 3. So if you wanted to get the term that came after that, subtract 3 again, and negative 14, and you can get the next term. We're going to come back to this type of sequence in the next section when we talk about arithmetic sequences. Arithmetic sequences all have what they call a common difference, the same number when you subtract the two consecutive entries. But what I want to point out right now is another way to write this formula. These a sub n's. Okay, so here's what I want you to notice. To get from A3 to A4, we took A3, which was negative 8, and subtracted 3 more. We took the 8 and we subtracted 3 more to get to the negative 11. We also could write that negative 8 was a sub 3 minus 3. Let me do this with another one. To go from A2 to A3, A3 was A2, which is negative 5, minus another 3. So what this means is, to get the third term, take the second term and subtract 3. To get the third term, take the second term and subtract 3 more. To get the next term, take the third term and subtract 3 more. To get the next term, take the fourth term and subtract 3 more. So a way to write this formula is this. To get the next term, the n plus first term is the term that comes after the nth term. I'll say that one more time. The n plus first term is the term that comes after the nth term. You take the nth term and subtract 3. So to get the fourth term, you take the third term and subtract 3. To get the third term, you take the second term and subtract 3. This formula is what they call a recursive formula, because each term is written as it depends on the previous term. The way we wrote the formula up here, this is what they would call an explicit formula. In order to figure out what the a sub n was, we just had to plug in whatever n is. So let's play around with these recursive formulas. This is an interesting problem because we can write the a sub n formula either as a recursively defined formula or as an explicitly defined formula. Before we leave this example, I want to show you one great thing about the explicit formula. If I asked you to find the 100th term of a sub n, and you were using the explicit formula, that wouldn't be so bad. Remember, to get the 100th term, you're just going to plug in n equals 100. So we would do a sub 100 equals negative 3 times n times 100 plus 1. Which, let's see, a little arithmetic here. That's negative 300 plus 1. So the 100th term is negative 299. If I asked you using only the recursive formula to figure out the 100th term, using only the recursive formula, that would be difficult. The 100th term is the 99th term and then subtract 3 more. But the problem is, I don't know the 99th term. In order to find the 99th term, I would need to know the 98th term and subtract 3 from that. And in order to know that, I'd have to know the 97th term and subtract 3 from that. So in order to find values that are very far along in our sequence, like the 100th term, the recursive formula is not very helpful. The explicit formula is terrific. But let's look at the recursive formulas in a little bit more detail. So let's write out the first 5 terms of the following sequence. So for our first example, let's do a sub n equals a sub n minus 1 all squared plus 2, and a sub 1 equals 1. I'm going to change my and to look more like an and. There we go. Not to be confused with the plus sign. Okay, so when we do recursive formulas, I have to give you a starting point. I have to tell you what is your first term in your sequence. That's why I have you write out the first 5 terms, because I give you number 1 for free. Okay, so we know the first term is 1, so finding the second term. Well, what our formula says to do is take the term that comes before that. So if you're finding the a sub 1, a sub n minus 1 means the term that comes before a sub 1. So take the term that comes before that, square it, and then add 2. So that will be the first term squared. That's the term that comes before the second term. Add 2, which is 1 squared plus 2, or 3. Okay, well, let's do the third term. The third term, using the formula, take the term that comes before the third term. Well, that's the second term. So second term squared, and then add 2. So the second term was 3. So 3 squared plus 2 is 9 plus 2, which is 11. Okay, the fourth term. Take the term that comes before that, that's the third term, square it and add 2. The third term, we had that was 11. 11 squared plus 2. 11 times 121 plus 2 is 123. One more. Fifth term. Take the term that comes before that, the fourth term, square it and add 2. Let's see, that is big. 123 squared plus 2. Well, 123 squared is 15,129 plus 2 is 15,131. 15,000, we scooch that over a little bit. 15,121. There are the first 5 terms of that sequence. So notice if I wanted to find, let's say, the 50th term for this, I would need the 49th term, square that, and then add 2. But I don't know the 49th term. In order to find the 49th term, I would need the 48th term. And in order to find that, I'd need the 47th term. So these recursive sequences are really common, but unfortunately they're a bit cumbersome for finding larger values along in your sequence. Okay, let's try another example. Okay, let's write out the first 5 terms again for the recursively defined sequence a sub n equals a sub n minus 1 times a sub n minus 2. And I always have to tell you what you need to start. So now I have to tell you, because I have a sub n is defined by the term that comes before that and the one that comes before that one, so a sub n minus 1 and 2 back, I have to give you the first two numbers. Well, if I'm only asking you to write out the first 5, that's great, because 2 are done for us. So we know a sub 1 is 2, and a sub 2 is 3. Okay, the formula says multiply the two previous terms. So a sub 3 would be a sub 2 times a sub 1. Or in other words, 3 times 2. Okay, a sub 4 is the term that comes before that, a sub 3, times the one that comes before that one, a sub 2. So a sub 3 we found out was 6, times the term that came before that is 3. So a sub 4 must be 18. And then one last one, a sub 5. Well, that's got to be the fourth term times the third term. 18 times 6. 18 times 6 is 108. So the fifth term is 108. Okay, great. One last example. Okay, I admit I geeked out a little bit here. I wanted to show you one of the coolest recursively defined sequences out there. This sequence is a really important sequence. It's called the Fibonacci sequence. And this sequence is defined like this. Each term is found by adding the previous two terms together. And generally, it starts with the first term is 0. Oops, and I made a mistake. The second term is 1, and I wrote that the first term was 1. I need to fix that. This should be a 2. Okay, so here's our first 5 terms. We already know that 0 is the first term and 1 is the second term. So the third term, oops, let me write that out here. The first term is 0. The second term is 1. The third term is 0 plus 1, so we get 1 again. The fourth term is the third term plus the second term, so 1 plus 1. The fifth term is the fourth term plus the third term, so let's see, 1 plus 2. Actually, let me write that in the correct order. The fourth term is 2 and the third term is 1. And because the sequence is so cool, I want to do 2 more. The sixth term is the fifth term plus the fourth term. So let's see, that's 3 plus 2, which is 5. Okay, now I'm just going to go up to my list here. So 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 3 is 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21, and so on. So that's not the first 5 terms. That's the first many terms. And the reason that this page is full of all of these images is each one of these images is related to the Fibonacci sequence. So right after this video, I'm going to post another video, not done by me, but done by somebody who is much better at video making than I. Vi Hart is her name, and it explains the relationship between this Fibonacci sequence here and all of the images that you see on the screen. It's a really cool sequence.